scientific and very detailed. So I should not try to do something which I am not good at. Although it's very good to see around this room some people from whom I have learned a few things. So if I'm presenting something which you already know, don't try to think that I'm trying to tell you something. It's just that I'm trying to put the context together. So I'll be presenting today a new approach towards structure elucidation. And coming from a software background, I wanted to spend some time to tell you what piece of technology or what software to use when. Because after a amount of times, we being vendors give you so much and then say, hold on, I've learned too much now. So I'll try to simplify that puzzle for you so that you can make a decision on what you need to do when you get across a situation. The content of this presentation, is it just me or is it going in and out?
Yeah, it's good.
Okay. So I'll just give you a very, very brief introduction of what we do. I'll take you through our case study. Are you able to hear me? No, of course, yes. Some examples, some publications, and what does the research fraternity think of the solutions which we bring to the market. So,
Your badge.
Alright. Is it better now? Good. So, we are a scientific software company which is based out of Toronto, in Canada. Wow. We have been serving the scientific community since 1994. So we'll be completing 2 decades of service to you all. So thank you very much. We are a global leader in providing software for structural elucidation, spectral prediction, spectral interpretation, spectral processing, spectral databasing, naming chemical property prediction. So we have been doing a lot of science.
I think it'll help if you just stay nearer to the podium. It'll be.
Yeah, it's like a bunker, not to fire at everybody. I don't like to stay behind the bunker. Okay, fine. Is it better now? So, a lot of you have already trusted in the solutions that we bring to the market. We now have about 390 customers in Asia and Pacific region outside of Japan. And as you would see, a lot have been distributed in India and China. So, since it's an NMR conference, I should be specific about what we do for NMR. So for NMR, we provide all these tools which are depending on what are your needs, be it processing and interpretation, or spectroscopically validating verification, which my friend just now presented, whether it is NMR prediction, whether it is creating a knowledge base, or a database, or a complete structural elucidation. So as the needs are growing, we have increased and we have come to a level where we can suffice all the needs which you would have towards the NMR. So as the need would increase, our solution should increase for you. On top of it, in the last 3 years, we have put in some effort towards automation. So we can do some automation, of course, before that. But how many of you know this? The NMR processor is free for academic use. You can take it, use it, generate reports which are journal ready, process, analyze, and interpret. Since now we have moved to a Spectrus processor, which is not only a processor for NMR, but also for MS, UV, IR, XRPD, DSC, TJ, etc. And of course, we now for the last 3 years have been providing some solutions for automation towards processing, towards verification, towards prediction, creating a knowledge base, and partially an automation towards elucidation. So before I go any further, since I'm from a software background, I wanted to ask people, why does anyone use any software? Of course, the first one is to save time, to enhance the quality of work so that the work when it is presented look more professional, to pass on the tedious and repeated type of work to the software so that the users could focus on what is more intelligent work. Of course, standardizing, collaboration, sharing the idea, connecting the ideas, and unbiased operation. And this is exactly what we try to do with our software. So let's take a case study. I don't know if it works. Were you able to hear me? I'm actually not used to being behind bunker. So this is a case study which I'm going to present, where what we did was we took a reference for a molecule which is cyclopropyne. It was published in China, and it is the reference which you can see. If you look at the structure, you would know why we picked this. In 2-dimensional, the structure looks like this, and in 3 dimensions, you could see it is multiplanar. It has 11 rings, and it is an unprecedented skeleton of carbon. So what we did was we wanted to test our structure elucidator, which is computer-assisted structure elucidation tool. We presented the same elucidation which we had come across in that publication. So this publication was for a natural product with an unprecedented carbon skeleton, with very limited 2D NMR and molecular formula, and the key correlations which the author had used is what we had in total to attempt with this elucidation. We just wanted to see how much can this help us. So what we took as an input was the molecular formula, which indicated 1 deficiency of hydrogen and 20 degrees of unsaturation. The structure is complex, as you saw. It is non-planar, it has 11 rings. The other thing is it contains a quaternary carbon with no neighboring heteroatoms with an anonymous carbon chemical shift at 69 ppm. So this is the data which we took. So this is the input which we brought to our structure elucidator, in addition to these correlations which were published by the author. You could see that the correlations from HMDC are here in green, and the correlations from COSI are these bonds in purple. So this is the information which we had. To start, it was suggested that the quaternary carbon which we see existed in the hybridization, which is sp3, and is connected with 3 nitrogen atoms from that formula, because the molecule contains an even number of sp2 hybridized carbons, which is 18, and we look at. The suggestion was confirmed by carbon NMR, and we did a prediction, and for several models it was confirmed that it is a sp3 hybridization. Now, based on this, we created a molecular connectivity diagram. I don't know how many of you use this term, but this is just a skeleton of the structure where we are connecting different atoms based on different techniques. So we created a molecular connectivity diagram, and as you would see, that the connectivities were not available for these. Now it was very well expected that when we are starting with a very limited information, the number of structures which are possible will be many. We compared the chemical shift of the generated structures. So we asked the software to generate structures which are possible from this molecular connectivity diagram. And then we put a restriction that any molecule which has more than 4 ppm difference between the carbon chemical shift, which is calculated, versus the theoretical or the experimental, it will reject. So in the results we found that after 90 hours of compute time, the software explored 3.7 million structures. Out of this, it selected only 16 unique structures which it thought were corresponding and close to the structure and had less than 4 ppm deviation. And out of this, the closest match which the software ranked was actually the right structure. So why did we use this? Why did we pick this example? The reason we picked this example is that the message which we want to drive here was, please do not leave any stone unturned. When you're working in your lab, several times you find good matches. 1 also looks good, 2 also looks good, 3 also looks good. Compare all of them. and of course, rank them which one is the best match. As you must have seen, that the structure which we did here was quite a complex one. This is already done humanly. So why did we do this? We did this just to show that humanly it would take a lot of effort to explore these many chemical structures. And it would need a lot of work to find which one fit and which one is the best one. Just to show this. And these are the top 3 chemical structures which the software found, and this is the correct structure. Now, some may say, well, I like it. You solved a very big problem, but I do not deal with these type of structures. Or, how does it relate to me? I don't work with natural products. I work with APIs. I work with specialty chemicals. And also tell me what to use then. So I have a question for all of you, for a change. Which one is faster? This or this? May I take 30 seconds to ask around. Which one do you think is which? How many of you think cycle is the faster or bicycle is the faster? Can you please raise your hand? My old friend, yes? How many of you think the car is the faster? How many of you think the car is the faster? No one thinks? Exactly. Exactly. So the answer is by which the work can be done faster. If I'm living in IIT Mumbai and I need eggs for my breakfast, I definitely want to take my bicycle, go to the grocery shop, get the eggs and come back. But if I live with my family, I need to get groceries for the month. I need to go to Heiko. So I need a car. So the answer is, you should decide depending on the work which you're doing. How far you have to go, how much load you have, how fast you want to start, how fast you want to come back, and so on. And that's exactly what is the point. That for different tools, you should not use, for different requirements, you should not use same tool. So the choice is yours. You may pick, I'm trying to derive a correlation, different techniques with this. It's up to you which one you would want to use and go with it. So now the question is, when does the workload increase for all of you? So the workload increases when the number of possibilities of structure are too many. And this happens when the data has limited information or when the experimental data has ambiguity. All of you are experts here, and I'm sure you must have seen artifacts. You must have seen a carbon showing 6 correlations, which you know is not correct. You have to drop at least 2 correlations if you've seen 6. Or sometimes you see artifacts and you need to find out the right peaks. Sometimes the information from one experiment needs to be confirmed with the other one. That's when the work increases, because you need to bring both of them together, extrapolate information from one to the other. How many of you are from the pharma industry? Okay, few of them. Sometimes the structure of the starting material is a curse, because you always think it's an impurity, it should be structurally related, but it is not. And sometimes, when you deal with natural products, so how many of you are dealing with natural products? Quite a few of them. So this is when the work increases. So here's my suggestion that when the molecule is small, just a processor is good enough for you to say, okay, NMR, 2 protons, 5 here, aromatic region, done, move on. When it is a little bit more complicated, when you want to connect information from one to the other, you want to be able to calculate a spectrum in the background and compare, you should use our structures processor or a predictor to compare experimental versus the predicted one. Here is another example when the workload increases. Let's say, for example, I have a molecule with mass 188. If I look at these four elements, the number of molecular formulas possible are 97. Now, how many of you want to work with 97 molecular formulas? I'm sure no one. Then why do we do NMR? The reason we do NMR is that the moment we cross 10 carbons, the number of isomers possible for that is too many. And the reason we want to use software is that if you want to evaluate 4,000 possibilities, the software can generate those 4,000 possibilities in less than 2 minutes. And this is something I would say you must take advantage of compute power to be able to look at everything, and as I said, leave no stone unturned. The other thing is, sometimes, and I'm sure people who have worked in natural products would have agreed, you spend 3 weeks elucidating the structure, and then you say, oh yeah, I know this one. It is published there. And then you realize that all the work that you did for 3 weeks was really kind of lost. So my recommendation would be to search before you elucidate. To provide you with a large library of experimental data and a large library of chemical shift which you could search. My advice to all of you would be that all the work which you do, you must create a knowledge base of your own, wherein you can bring in the structure and the associated NMR and the MS and all the other analytical experiments in one place. And then comes structure elucidator. So as you would see that for a complete elucidation you need to work with several experiments, if not several techniques. So here is a small snapshot of what would happen. You would see that with the help of our cozy data, the software has established these connectivities. With the help of ROSI, these. HMBC, these. So the software has actually put together all different connectivities from different techniques and brought them together in one place. And then you say, how about if my mass is this and I want to generate a molecular formula? You generate a molecular formula, and now you would see you have the elements. And then you start working with it, create a molecular connectivity diagram. Now based on this, it will generate thousands of structures. And that's what you would have to try to elucidate. So the software is trying to unlock this lock with 1,000,000 keys. And then it comes back to you, which is the key which unlocks this. And then you can solve stereochemistry. Imagine if you were to work with this. It would take a lot of time. Not that it cannot be done manually, it can be. But imagine if you were able to reduce the time in arriving at these structures. That's what you must do. I have another quote to make here. And that is more true for natural products and sometimes forced degradation. All strands we have seen are white. And therefore, all strands are white. Is that correct? Maybe not. Because sometimes you may come across a black swan. Which means, again, yes, you are going in the right direction, but if there was something which would help you see something which you had not thought of, a stone which you left to turn. I'll quote Dr. Dave Faulkner. He said, at the end, the proof of the structure is a hypothesis which you prove, which can of course be proven wrong. The reason is, if you're working with a C15, these are the number of possibilities which you can look at. So my conclusion is that different users would solve the structure differently, depending on the complexity, depending on the load of the work. So whether you want to use a bicycle, a motorbike, a car, it is your choice depending on the complexity and the number of multiple structures which are possible. So we are here to help you at several stages of your work. Whether it is processing, we can help you everything which you need for the processing, interpretation, verification where you would want to assign a structure to a spectrum or compare the match between a spectrum and a structure. Whether you want to create a knowledge base, you want to search a knowledge base, you want to integrate a knowledge base, or you want to do a complete elucidation. There are tools available for everything. You must use them all. Many times people ask me, okay, if you have to use all, should we need to buy all for all? No. So maybe you can look at, if you have 100 chemists in your lab, you look at basic 400 chemists. If you have 5 group leaders, or if you have 1 characterization expert. So this is how you would go. So here are some of the credentials which I have, which I wanted to present. A couple of years ago, this journal became all-time highest access journal in Journal of Cheminformatics, which is about structural elucidator. Dr. John Johnson in SMASH presented this. Steve Sheehan presented this. Mikhail Ilyasberg presented this. Gary Martin presented this. Anna Kudina presented this. And there are some examples. So there is a document which is available on request, which I put together, which contains 27 publications on such elucidation, which were created from data from like Journal of Natural Products and so on, with 11 peer-reviewed publications. Here, the tabular data was entered and the structures were solved. Some of these publications are, before I go, so if the software is for small molecule, how big can it get? So the largest molecule which we have done is about 1500 Daltons. We were able to look at something because we suggested a molecular formula, and then we did what we do for the elucidation. The good news is that this is a marine product and it is for an Indian pharma company. I think I have the gentleman in this room also who know about this elucidation. Anyway, so we can go up to 1500 Daltons. These are some of the examples which are there. The publication is also available at our stall. This is from the Journal of Natural Products in 2002. I'll not go through exactly what it is because you can ask for this document. You can see that the molecules which we have elucidated are quite large and difficult to do. So we were able to do the same thing which were done manually, and we were able to save time. So at the end, we at AC Labs are providing software for you all in various techniques and in various departments. We today discussed about this. Maybe when we meet next time in your lab, in your institute, we can talk more about that. So with this, I would like to acknowledge some of my colleagues: Kirill, Ryan, Kareem, Joe, Arvind, Nancy, and Nilesh, who are with me here today at our booth. And of course, a big thank to this gentleman, this young man who is 75 years young. He still comes to our office 9 a.m. till 5 p.m. He's still working. And he's the one who actually created the prototype of structural elucidator. Thanks a lot for your time. I'm ready for questions and answers. If you want, you can reach out to me. Really appreciate your patience. Thanks a lot.
Lot of good questions and clarifications. Okay, thank you, Dr. Bhagchandani. When we move on to the